I want to show you an interesting reaction of alkenes that occurs selectively at allylic positions. When an alkene is treated with NBS and light, bromine selectively appears in place of a hydrogen at the allylic position. Very first thing you'll ask is, hey, what is NBS? And let me show you. It's a sort of complicated looking structure. It has especially weak nitrogen-bromine bond, so light can selectively cleave that bond, which under these conditions results in two things: a low concentration of bromine, molecular bromine, and a catalytic amount of bromine radicals. You could already guess that the reaction at the allylic position is initiated by reaction with a bromine radical. But there's another interesting part of this reaction I want to tell you first. Now we notice right away that there are two CH2 positions in the molecule where the bromine radical could react. The allylic position is selectively reactive, and we don't see reaction at this other CH2 position. The reaction is so much slower at this position that we see no product. In addition to this regioselectivity, there's another interesting thing about this reaction. It makes a second product. The second product has the double bond shifted over in the bromine at the other end of an allylic system. Now, putting this selectivity together with the fact that two products result, we can draw a mechanism that makes sense of all this. We can picture reaction at the allylic position using our air pushing to track bond formation with this electron contributing and one of these electrons contributing, and the other one of these electrons remaining at the allylic position. This forms an allylic radical which has two resonance structures. Notice that all we have to do is envision one of these electrons slipping over here to pair with this electron to make the second resonance structure. So we can write two resonance structures for this intermediate, which can react with molecular bromine at this allylic position or with molecular bromine at this allylic position. And recall that we say when there are two possible resonance structures that are reasonable, they both will contribute to the way the structure looks, and the structure will be more stable than normal, to explain why we have the regioselectivity at the allylic position. And the fact that we can write two resonance structures with electrons at two different places accounts for the fact that we have two different products. MO theory leads us to the same conclusion. Take a look. Formation of the intermediate allylic radical gives us a pi system that has 3 electrons. And when this allylic radical reacts, it will react with a non-bonding pi2 orbital that contains a single electron. And where is that electron? Well, that electron is at the two ends of the allylic system, this carbon and this carbon, but never the central carbon. So when it reacts, of course it will react at both ends because there's a probability of finding the electron at either end, but never in the center. So our MO theory tells us that we should expect two products from this allylic radical intermediate. And whether you use MO theory or resonance structure theory to explain the result, either way, NBS creates small amounts of bromine and bromine radicals, which react specifically at the allylic position, ultimately substituting bromine at both ends of the allylic system, resulting in two products.